Imagine drifting through the silent expanse of space, past rocky remnants of our solar system's birth asteroids, those ancient time capsules hurtling through the void. These cosmic wanderers aren't just barren chunks of rock and metal. They're hiding secrets so strange, so utterly unexpected, that even the most seasoned scientists have been left speechless. What if I told you that some of these asteroids carry materials that shouldn't exist, or that they might hold clues to life's origins, or even our future? Today, we're diving deep into 25 of the most bizarre, mind-bending discoveries ever made on these celestial nomads, and trust me, by the end, you'll never look at the night sky the same way again. Think about this for a moment. Asteroids are like the universe's forgotten treasure chests. They've survived billions of years of chaos collisions, solar winds, the violent tug of planets, yet they've preserved artifacts that defy logic. From metallic structures that shouldn't form naturally to organic compounds that hint at the building blocks of life, every new mission to an asteroid seems to rewrite the textbooks. And here's the kicker, we've barely scratched the surface. Each discovery peels back another layer of mystery, leaving us with more questions than answers. What else is lurking out there, waiting to be found? This isn't just about scientific curiosity, it's about unraveling the story of us. Asteroids might hold the key to understanding how water arrived on Earth, how life began, or even how humanity could one day survive among the stars. Some of these findings are so bizarre, they sound like science fiction. Alien minerals, unexplained magnetic fields, even the possibility of ancient microbial fossils. So buckle up, because we're about to embark on a journey through the strangest, most awe-inspiring discoveries ever made on these cosmic relics. By the time we're done, you'll see why scientists are racing to uncover the truths hidden in these rocky enigmas, and why the next big revelation could change everything. One of the most startling revelations from asteroid research is the presence of complex organic molecules, carbon-based compounds that form the foundation of life as we know it. Take the near-Earth asteroid Ryugu, for example. When Japan's Hayabusa 2 spacecraft collected samples from its surface, scientists didn't just find simple hydrocarbons, they uncovered a rich cocktail of amino acids, the very building blocks of proteins. These molecules shouldn't survive the harsh radiation of space, yet there they were, preserved like cosmic time capsules in Ryugu's ancient rubble. What makes this discovery so groundbreaking? For decades, we assumed life's ingredients had to form on Earth, but asteroids like Ryugu suggest otherwise. They could have been cosmic delivery trucks ferrying the raw materials for life across the solar system. Imagine the same amino acids found in your body might have first hitchhiked here on a space rock billions of years ago. And it's not just Ryugu, similar organics have popped up on asteroids like Bennu and even fragments of the meteorite that crashed into Murchison, Australia in 1969. Each finding chips away at the old theory that life's chemistry is unique to Earth. But here's where it gets even stranger. Some of these molecules don't behave the way traditional chemistry predicts. On certain asteroids, organics arrange themselves into structures so complex, they blur the line between chemistry and biology. Scientists have spotted microscopic patterns resembling primitive cell membranes and energy capturing molecules similar to those in living cells. No, we haven't found alien microbes, but these discoveries hint that the universe might be pre-programmed to assemble life's scaffolding under the right conditions. The implications are staggering. If asteroids routinely carry these compounds, then the seeds of life could be scattered everywhere, just waiting for the right planet to nurture them. This shifts the search for extraterrestrial life into hyperdrive. Instead of hunting only for Earth-like planets, we might look to asteroids as cosmic recipe books, holding clues to how life sparks and spreads. Every sample we bring back rewrites the story, proving that the boundary between space chemistry and biology is far thinner than we ever imagined. If amino acids rewrote the book on life's origins, then the discovery of water ice on asteroids tore out entire chapters and started fresh. Take Ceres, the largest object in the asteroid belt, once dismissed as a dry, inert rock. When NASA's Dawn spacecraft approached it in 2015, the data stunned researchers. Ceres wasn't just hiding water ice beneath its surface. It was practically oozing it. Bright, reflective patches near its poles turned out to be massive deposits of nearly pure ice, some exposed in dramatic landslides. And Ceres isn't alone. Smaller asteroids like Themis and 24 Themis have also revealed spectral signatures of water ice clinging to their surfaces, defying expectations that the sun's heat should have vaporized it billions of years ago. This isn't just about ice existing where it shouldn't. It's about rewriting the solar system's history. For decades, scientists assumed Earth's water came solely from comets, those icy wanderers from the outer solar system. But asteroids like Ceres suggest a radical alternative. The inner solar system may have been far wetter than we thought. Imagine a time when water ice wasn't rare in the asteroid belt but commonplace. Collisions could have shattered countless icy asteroids, scattering their fragments toward Earth during the planet's fiery infancy. Suddenly, the oceans in your backyard might trace their lineage to these unassuming space rocks. The practical implications are just as staggering. Water isn't just for drinking, it's a gold mine for future space exploration. Split it into hydrogen and oxygen, and you've got rocket fuel. Combine it with carbon from asteroids, and you can grow food in space. Ceres alone might hold more fresh water than all of Earth's lakes. No wonder space agencies eye these asteroids as cosmic pit stops for missions to Mars and beyond. But here's the twist. Some of this ice behaves unlike anything on Earth. On Ceres, Dawn spotted mysterious bright spots in Ocata crater. Not just ice, but salts mixed with water in a complex dance of evaporation and recondensation. These aren't static reservoirs, they're active, almost alive, reshaped by subtle geologic processes over millennia. It hints at a hidden world of subsurface brines where liquid water might still linger in insulated pockets. So what does this mean for the search for life? If liquid water persists in the asteroid belt, even in tiny amounts, it raises the tantalizing possibility of habitable niches. Not for complex organisms, perhaps, but for extremophiles, the hardy microbes that thrive in Earth's harshest environments. Suddenly, asteroids aren't just relics. They could be way stations for life, ferrying not just its ingredients, but perhaps even its faintest whispers across the cosmos. Now picture an asteroid so bizarre, it gleams like a celestial cannonball in the void, not covered in ice or dust, but forged almost entirely of metal. Meet 16 Psyche, a 200-kilometer-wide relic orbiting between Mars and Jupiter that's unlike any other asteroid we've found. While most space rocks are rubble piles or icy fragments, Psyche's surface reflects radar-like polished steel, with spectral readings suggesting it's packed with iron, nickel, and even traces of gold. This isn't just a random hunk of space debris. Scientists believe it could be the exposed skeleton of a failed planet's core, ripped bare by cosmic violence billions of years ago. Why does this matter? Think of Psyche as a time machine. Planetary cores, including Earth's, are buried so deep under thousands of kilometers of rock that we'll never directly sample them. But Psyche offers a freakish shortcut, a fossilized core we can study from orbit. The leading theory suggests it was once the molten heart of a Mars-sized protoplanet, shattered in the solar system's chaotic youth. Collisions may have stripped away its rocky mantle, leaving only this metallic husk behind. If true, every crater on Psyche's surface is a window into processes that shaped worlds, from Earth's magnetic field to Mercury's oversized iron core. NASA's Psyche mission, launching this year, aims to test these theories. The spacecraft will map the asteroid's composition with gamma-ray spectrometers, measure its gravitational quirks, and even search for remnants of ancient magnetic fields, ghosts of the dynamo that might have once churned in its molten depths. But here's the twist. Some researchers argue Psyche wasn't a core at all. Alternative theories suggest it could be a pile of metallic rubble from a different kind of cataclysm, perhaps the residue of a massive impact that fused metals into strange new alloys. Either way, the implications are profound. If Psyche is a planetary core, it could rewrite our understanding of how terrestrial planets like Earth assembled. Its metal content, estimated at enough iron to cover global demand for millions of years, also fuels wild speculation about asteroid mining. Yet the real treasure isn't the gold or nickel. It's the realization that our solar system's infancy was even more violent and unpredictable than we imagined, with worlds torn apart and their innards scattered across the void. Psyche isn't just a scientific curiosity. It's a gravestone for a planet that never was, and a reminder that the universe favors chaos over neat, orderly creation. And the strangest part, Psyche might not be alone. Telescopes have spotted dozens of other metallic asteroids lurking in the belt, each with its own twisted origin story. That changes everything. Instead of being freakish outliers, these objects could represent an entire class of cosmic artifacts, silent witnesses to the brutal collisions that sculpted the planets we know today. As we gear up to visit them, one thing's certain: the asteroid belt isn't just debris. It's a junkyard of planetary corpses, and their secrets are only beginning to surface. While most asteroids appear as lifeless hunks of rock or metal floating through space, some hide an invisible secret, mysterious magnetic fields that defy explanation. These aren't the powerful forces we associate with planets like Earth, but faint, ghostly imprints locked within the rocks themselves. When scientists first detected these signals from asteroids like Braille and Eros, the discovery sent shockwaves through the astronomy community. How could these small, seemingly inert objects retain magnetic fields billions of years after their formation? The answer might lie in the violent infancy of our solar system. One leading theory suggests these asteroids were once part of much larger bodies, protoplanets with molten metal cores that generated magnetic dynamos, just like Earth's does today. When these ancient worlds shattered in catastrophic collisions, fragments of their cores could have cooled rapidly, freezing their magnetic fields in place like cosmic snapshots. Picture a drop of molten iron suddenly solidifying mid-spin, preserving the exact alignment of its atoms at that moment. These asteroids might be carrying the last whispers of magnetic fields that haven't existed for 4.5 billion years. But there's a twist. Some of these magnetic signatures don't match planetary cores at all. The asteroid Itokawa, visited by Japan's Hayabusa mission, showed patches of magnetism far stronger than its size should allow. Researchers now suspect micrometeorite impacts could have superheated tiny portions of its surface, realigning minerals to act like microscopic compass needles. It's as if these space rocks have been tattooed by countless cosmic collisions, each leaving behind a faint magnetic fingerprint. These discoveries aren't just academic curiosities, they're rewriting solar system history. By comparing asteroid magnetism with meteorites found on Earth, scientists have uncovered a startling pattern. Many seem to align with a hypothetical, lost magnetic field that may have permeated the early solar system, generated by the young sun's turbulent plasma. If confirmed, this means asteroids could preserve clues about environments that vanished before Earth even formed. The implications stretch beyond our solar system. If even small bodies can retain ancient magnetism, it suggests a universal method for decoding the magnetic past of exoplanetary systems. Future missions might use asteroids as Rosetta Stones, translating the hidden language of magnetic fields across the galaxy. Every faint signal we detect is another piece of the puzzle, revealing how chaos and chance shape the worlds we call home. Now consider this cosmic ballet, two asteroids locked in an eternal dance, circling each other as they hurtle through space. Binary systems like Didymos and its tiny moon Dimorphos aren't just celestial curiosities. They're cosmic puzzles that challenge our understanding of how asteroids form and evolve. When NASA, a DART mission, intentionally slammed into Dimorphos in 2022, it wasn't just a test of planetary defense. It revealed secrets about how these gravitational duos behave under extreme conditions and why they might be far more common than we ever imagined. How do such delicate pairings form in the chaos of the asteroid belt? One leading theory points to the Yorp effect, a quirky phenomenon where sunlight unevenly heats a spinning asteroid, slowly accelerating its rotation until centrifugal force flings material into space. Over millennia, that ejected rubble can coalesce into a small companion, creating a natural satellite like Dimorphos. Other binaries might form through catastrophic collisions, where a high-speed impact shatters a larger asteroid, leaving two stable fragments gravitationally bound. The diversity is staggering. Some binaries resemble spinning tops with tiny moons, while others, like Antiope in the main belt, are nearly equal in size, orbiting a shared center of gravity like dumbbells in the void. Their dynamics are even stranger. Unlike planets with their stately orbits, binary asteroids often exhibit chaotic wobbles and tumbling motions. Dimorphos, for instance, orbits Didymos in just under 12 hours, a rhythm so precise that NASA used it as a celestial stopwatch during the DART impact. But here's the twist. Post-collision observations showed Dimorphos' orbit had shortened by over 30 minutes, proving we could alter an asteroid's trajectory with human-made force. This wasn't just a victory for planetary defense. It unveiled how loosely packed these rubble pile moons really are, responding to impacts like cosmic sandbags rather than solid rock. Beyond defense, binary systems serve as natural laboratories for studying gravity's subtleties. Their mutual orbits reveal hidden details about mass distribution, internal structure, and even the faint influence of solar radiation pressure. Some, like the Patroclus-Menoetius pair in Jupiter's orbit, are so pristine they're considered time capsules from the solar system's earliest days. Others hint at future resource potential. Imagine mining a binary system where materials could be shuttled between partners with minimal energy. Yet the biggest revelation might be their ubiquity. Current estimates suggest 1 in 6 near-Earth asteroids could be binaries or even triples, a statistic that reshapes how we assess impact risks. If many asteroids travel with companions, deflection strategies must account for multiple objects. Every binary we study peels back another layer of their mystery, proving that even the simplest-looking space rocks can harbor astonishing complexity. As missions like Ceres here prepare to visit Didymos post-impact, one thing's clear: these cosmic duos aren't just passing oddities. They're keys to understanding everything from planetary formation to humanity's survival among the stars. Beneath their rugged exteriors, many asteroids hide a shocking secret. They're not solid rocks at all, but fragile piles of cosmic rubble, barely held together by gravity. Imagine a mountain-sized snowball, loosely packed and filled with voids, spinning through space. This rubble pile structure, first confirmed by Japan's Hayabusa mission to asteroid Itokawa, has turned our understanding of these objects upside down. Instead of monolithic boulders, asteroids like Bennu and Ryugu resemble floating gravel heaps with surfaces that crumble under the slightest pressure. When NASA OSIRIS-REx spacecraft attempted to collect samples from Bennu, its touchdown caused an unexpected explosion of debris, proof that these asteroids are more like celestial sandcastles than solid stone. The implications are staggering. Rubble piles behave unpredictably, especially when nudged by gravitational tugs or sunlight. The Yarkovsky effect, a phenomenon where uneven heating from the sun gradually alters an asteroid's path, becomes amplified in these loosely bound structures. A small push over millennia could send a rubble pile veering toward Earth, with its fragile nature making deflection efforts tricky. Traditional nuclear deterrents, for instance, might simply blow apart a rubble pile without changing its overall trajectory, creating a shotgun blast of debris instead of a single threat. But here's the twist: their instability might also be their weakness. Missions like DART proved that kinetic impacts can significantly alter a rubble pile's orbit, precisely because they're so loosely packed. When NASA spacecraft hit Dimorphos, it didn't just nudge the asteroid. It unleashed a debris plume so massive it acted like a natural thruster, amplifying the push. This suggests that early intervention could one day steer rubble piles away from Earth using their own fragility against them. Beyond planetary defense, these asteroids hold clues to the solar system's violent past. Their porous structures likely formed from the debris of ancient collisions, making them cosmic archives of catastrophic events. Some, like Bennu, contain pristine material dating back to the solar system's birth, preserved in their loosely bound interiors. Others may even harbor pockets of water ice trapped between rocks, shielded from sunlight for eons. Yet the biggest mystery remains how these delicate agglomerations survive at all. Without cohesive strength, they should disintegrate under centrifugal force or tidal stresses, yet they persist, defying expectations. Some scientists speculate microscopic forces like van der Waals attraction or electrostatic cling might help hold the rubble together like a pile of magnets resisting collapse. Others suggest they're constantly reforming, with new debris replacing ejected material in a slow-motion cycle of destruction and renewal. As we prepare to visit more of these cosmic puzzle boxes, one thing's clear: rubble piles aren't just oddities. They're testaments to the delicate balance between chaos and cohesion in the universe, and a reminder that sometimes the most unassuming objects hold the deepest secrets. Among the countless asteroids drifting through our solar system, a rare few bear the scars of ancient fires, evidence that these seemingly inert rocks were once home to volcanic fury. Take Vesta, the second largest body in the asteroid belt. Unlike its rubble pile neighbors, Vesta's surface tells a dramatic story of molten lava flows, towering mountains, and a colossal impact basin so deep it exposes layers of the asteroid's crust. When NASA's Dawn spacecraft mapped Vesta in 2011, it revealed a world more akin to the rocky planets than a typical asteroid, complete with a differentiated interior, a layered structure with a metal-rich core, mantle, and basaltic crust. This isn't just geology, it's a fossilized record of the solar system's adolescence, when small worlds blazed with internal heat before time froze them in place. What makes Vesta's volcanoes so extraordinary? They weren't like Earth's fiery peaks. Instead, they likely erupted in low-energy, effusive flows. Imagine thick, syrupy lava oozing across the surface, leaving behind vast plains of solidified rock. These volcanic remnants, now preserved as dark, patchy regions called Vestoids, contain minerals like pyrozene and olivine that only form under intense heat. But here's the twist: Vesta's volcanic activity didn't last billions of years like Earth's. It was a fleeting outburst fueled by the decay of radioactive isotopes like aluminum-26, a short-lived element abundant in the early solar system. This cosmic clock suggests Vesta's fires burned bright and fast, perhaps for just a few million years before its engines sputtered out. The implications ripple far beyond one asteroid. Vesta's volcanic past hints that dozens of similar protoplanets once simmered with activity in the asteroid belt. Some, like the parent body of the HED meteorites found on Earth, may have shared Vesta's fate, shattered by impacts, their fragments scattered across the solar system. Others could have grown larger, evolving into planets like Earth or Mars. Vesta, then, is a snapshot of a road not taken, a glimpse of what might have been if Jupiter's gravity hadn't disrupted the asteroid belt's evolution. Yet the most startling revelation lies in Vestan lava's composition. Samples from HED meteorites believed to be chips off Vesta's block contain water-bearing minerals. This suggests that even in these fiery environments, water persisted, perhaps trapped in the asteroid's interior or delivered by icy impacts. It's a paradox, a world shaped by heat, yet harboring the ingredients for life's chemistry. As missions like Lucy explore more asteroids, Vesta stands as a reminder that the early solar system was a cauldron of geologic diversity. From molten metal cores to icy volcanoes on worlds like Ceres, asteroids defy simple categorization. They're not just debris, they're the surviving chapters of a story where every rock, every crater, and every mineral grain whispers secrets about how planets live, die, and occasionally leave behind echoes of their brief, fiery youth. Deep in the cosmic void, certain asteroids carry a glittering secret. Their surfaces are studded with carbon-based minerals so hard, so brilliantly structured, they rival Earth's diamonds. These aren't the gemstones of jewelry stores, but something far stranger. Lonstellate, a hexagonal diamond that forms under pressures and temperatures only interstellar collisions can produce. When scientists first detected its signature in fragments of the Alma-Ata-Sita meteorite, a shattered asteroid that rained down over Sudan in 2008, it confirmed what they'd long suspected. The chaos of asteroid impacts doesn't just destroy, it forges. How does space turn carbon into diamond-like structures? Picture two asteroids colliding at staggering speeds 15–20 kilometers per second. At those velocities, graphite layers in their crusts don't merely melt, they realign into ultra-hard lattices, preserving a snapshot of the exact moment of impact. Lonstellate's unique hexagonal structure actually makes it theoretically 58% harder than terrestrial diamonds, though most space-formed samples are microscopic. But here's the twist. Some asteroids like Bennu and Ryugu contain pre-solar graphite grains that underwent this transformation multiple times over billions of years, creating layered time capsules of cosmic violence. Beyond scientific curiosity, these minerals spark practical dreams. Industrial applications for super-hard materials range from next-generation drill bits to quantum computing components. On Earth, we manufacture synthetic diamonds under immense pressure, but asteroids offer them ready-made, with some space rocks potentially harboring tons of lonstellate. The catch: mining it would require pinpointing the rarest of asteroids, those that survived cataclysmic impacts intact enough to preserve their diamond factories, yet fragmented enough to expose them. The discovery also reshapes our view of carbon's cosmic journey. These minerals prove that carbon life's backbone doesn't just passively exist in space. It transforms, crystallizes, and endures, cycling through asteroids like a celestial recycling program. Some researchers even speculate that lonstellate's durability could help protect organic molecules during atmospheric entry, delivering life's ingredients safely to young planets. Yet the most tantalizing possibility lies in what we haven't found. If impacts create diamond-like materials, what other exotic phases of carbon might exist in the asteroid belt? Hypothetical forms like BC8 carbon, predicted to be even harder than diamond, could lurk undiscovered in impact craters we've yet to sample. Every asteroid visit peels back another layer, revealing a universe where the line between destruction and creation is thinner than we ever imagined, and where the rubble of ancient collisions might hold the keys to tomorrow's technologies. When we think of asteroids, we usually picture dull gray or brown rocks, but Bennu shattered that expectation with its bizarre blue hue. This near-Earth asteroid, visited by NASA's OSIRIS-REx mission, isn't just a monotonous space boulder. Its surface glimmers with an unexpected cobalt tint, especially in regions less weathered by solar radiation. At first glance, it seems like a cosmic glitch, but these color variations are anything but random. They're geologic fingerprints, revealing hidden chapters of Bennu's 4.5 billion-year history. The blue patches hint at something extraordinary: pristine material, relatively untouched by the ravages of space. Most asteroids turn reddish over time, bombarded by charged particles and micrometeorites in a process called space weathering. But Bennu's bluer regions suggest areas where fresh, carbon-rich material lies exposed, perhaps recently uncovered by landslides or impacts. It's like peeling back layers of cosmic paint to find the original color underneath. Scientists suspect these unweathered zones might contain organic molecules in their purest form, offering clues to the asteroid's primordial composition. Bennu isn't alone in its chromatic oddities. The asteroid Phaethon, responsible for the Geminid meteor shower, dazzles with an eerie ultramarine sheen, so intense that researchers initially doubted their instruments. Unlike Bennu, Phaethon's blue isn't from preserved material but from extreme heat. This asteroid ventures closer to the Sun than Mercury, baking its surface to temperatures hot enough to vaporize metals. The result, a strange, glassy crust that scatters light in unusual ways, turning Phaethon into a celestial sapphire. Then there's the case of Cleopatra, the metallic, dog-bone asteroid whose radar reflections reveal a coppery red tint. That rusty color comes from iron-rich minerals oxidizing in space, yes. Even without Earth-like oxygen, trace amounts can react over eons. Cleopatra's hue suggests it's been slowly rusting since the solar system's birth, its metal content leaching into the surrounding regolith like an ancient cosmic nail left out in the void. These colors do more than dazzle, they decode an asteroid's story. Reds and browns often signal iron and organic compounds, while blues may point to water-altered minerals or exposed subsurface layers. Some asteroids, like Ryugu, even show mottled patterns, dark, carbon-packed areas alongside brighter stretches of silicate rock, like a cosmic quilt stitched together by collisions and cosmic erosion. The biggest surprise, these palettes aren't static. Japan's Hayabusa 2 mission watched Ryugu's surface darken slightly after firing an impactor into it, proving that even subtle disturbances can alter an asteroid's color. It's a reminder that these worlds are dynamic, their hues shifting with every impact, solar flare, or gravitational tug. So next time you gaze at the night sky, remember, the asteroid belt isn't a grayscale wasteland. It's a swirling gallery of cosmic art, where every shade tells a tale of violence, survival, and the quiet persistence of matter across billions of years. And we've only just begun to interpret its vivid language. Some asteroids might resemble cosmic sponges more than solid rocks, laced with vast caverns and hollow interiors that defy our expectations of how space rubble behaves. Take Bennu, the Rubble Pile asteroid visited by NASA OSIRIS-REx mission. When scientists measured its density, they got a shock. Despite its substantial size, Bennu's mass was far lower than predicted, suggesting up to 50% of its interior could be empty space. This isn't just a fluke. Similar measurements of asteroids like Itokawa and Ryugu point to the same bizarre conclusion. These aren't monolithic boulders, but fragile labyrinths of boulders and voids held together by the faintest gravitational grip. How do these cosmic Swiss cheeses form? The leading theory points to catastrophic collisions in the asteroid belt's violent past. When two asteroids slam together at astronomical speeds, they don't just crack, they shatter, sending debris flying in all directions. Some fragments eventually reaccumulate, but not uniformly. Gravity pulls the largest chunks together first, creating a loose framework with gaps between boulders too wide to fill. Over time, smaller particles might settle into some voids, but many remain, preserved like bubbles in cosmic foam. This process explains why rubble pile asteroids often have such low densities. They're less like solid mountains and more like orbiting gravel piles with cavernous interiors. But here's where it gets stranger. Some hollow spaces might not be accidental. On asteroids like Psyche, scientists suspect ancient volcanic activity could have played a role. If metallic lava flowed beneath a crust and later drained away, it might leave behind tunnel-like voids. Think of the hollow tubes found in Hawaiian lava fields, but on an asteroid-wide scale. Even more intriguing are the contact binary asteroids, where two space rocks gently merged without fully compacting, creating a dumbbell shape with a hollow neck. These structures are so delicate, a firm handshake's worth of force could disrupt them. The implications ripple across multiple fields. For planetary defense, hollow asteroids behave unpredictably when nudged. Their porous structures might absorb impacts like a sponge or fracture violently under pressure. Mining ventures face hurdles too. Extracting resources from cavernous bodies could require entirely new techniques, like injecting stabilizing materials before drilling. Even our understanding of solar system history gets a twist. If hollow asteroids are common, it suggests the belt was shaped by gentler accretion events than we thought, collisions where rubble settled like snowflakes rather than compacting into dense rock. Perhaps the most tantalizing possibility lies in these voids' potential as natural shelters. Future explorers might one day anchor bases inside asteroid caverns, using the rock walls as radiation shields. Some models even suggest certain hollow spaces could trap water ice in perpetual shadow, creating ready-made reservoirs for deep space missions. Yet the biggest mystery remains unanswered: just how extensive these subterranean networks are. Radar scans from upcoming missions could map their shadows, but we won't know for sure until we drill. Every new discovery peels back another layer, revealing asteroids not as dead relics, but as dynamic worlds where emptiness holds as many secrets as solid ground. Picture an asteroid not as a lifeless boulder, but as a cosmic sandcastle crumbling in slow motion, constantly shedding dust into the void. This isn't science fiction. Take Itokawa, the peanut-shaped asteroid visited by Japan's Hayabusa mission. Close-up images revealed its surface isn't solid rock, but a loose collection of gravel and boulders with virtually no fine material between them. So where did all the dust go? The answer lies in the relentless tug of sunlight and the subtle push of solar wind. Over millennia, these forces have been quietly stripping Itokawa of its smallest particles, sending them spiraling away to join the vast reservoir of interplanetary dust that drifts throughout our solar system. This process isn't unique to Itokawa. Dozens of asteroids, especially rubble pile types, exhibit similar behavior. Their weak gravitational hold, often just a millionth of Earth's, means even the faintest nudge can liberate surface grains. Thermal fracturing plays a role too. As these space rocks rotate, their sunlit sides expand while shadowed regions contract, creating stresses that crack surface material into ever smaller fragments. The result, a steady rain of dust particles, each no larger than a grain of sand, ejected into space to form what scientists call impact-generated debris clouds. But here's the twist: this isn't just random scattering. The dust follows precise dynamical pathways, some spiraling inward toward the sun, others getting trapped in orbital resonances with planets. Studies suggest a significant fraction of the micrometeorites that strike Earth's atmosphere every day, tons of material in total, originate from these asteroid dust factories. Some even end up preserved in Antarctic ice cores or buried in ocean sediments, where scientists can analyze their composition to trace them back to their parent bodies. The implications are staggering. First, it means asteroids aren't just static relics, they're active participants in the solar system's dust cycle. Second, their emissions create navigational hazards for spacecraft. The dust surrounding certain asteroids forms tenuous exospheres that could damage sensitive instruments during close encounters. Yet these same particles also serve as scientific gold mines. Missions like JAXA Destiny Plus, slated to fly by the dust-emitting asteroid Phaethon, aim to capture and analyze these grains directly, potentially revealing secrets about the asteroid's composition without ever landing. Perhaps most remarkably, this dust shapes planetary environments in ways we're only beginning to understand. When Earth passes through particularly dense streams, like those from asteroid-comet hybrids such as 320 Phaethon, we get spectacular meteor showers. Over geological timescales, accumulated asteroidal dust may have even delivered volatile elements to young planets, subtly influencing atmospheric chemistry. So the next time you see a shooting star, consider its origins. That fleeting streak of light might trace back to an unassuming asteroid, silently weathering away in the darkness, its lost fragments now igniting in our skies as celestial breadcrumbs marking its slow, inevitable dissolution. Far from being inert, these cosmic pebbles are dynamic contributors to the solar system's grand cycle of destruction and renewal. Buried within some asteroids are chemical fingerprints so exotic, they defy anything found in Earth's crust, isotopes forged in the heart of dying stars. When scientists analyzed grains from the asteroid Ryugu, they stumbled upon tiny crystals of silicon carbide with isotope ratios that screamed alien. These weren't just slightly different from Earth's chemistry, they were products of environments so extreme they could only originate from supernova explosions or the violent winds of red giant stars. The most shocking discovery, these isotopes are older than the solar system itself, preserved like cosmic fossils in the rubble of space rocks. How did these stellar relics end up trapped in asteroids? The story begins in the final moments of massive stars. When a supernova detonates, it floods space with newly minted elements including rare isotopes like xenon-124 or neon-22, which form under specific nuclear reactions. These atoms, ejected at nearly light speed, eventually mixed with the molecular cloud that birthed our solar system. But instead of blending uniformly, some clumped together, becoming microscopic time capsules embedded in the first generation of asteroids. The real enigma lies in their survival. Over 4.5 billion years, the solar system's chaos should have erased these delicate signatures. Yet asteroids like Ryugu and Bennu acted as cosmic refrigerators, their cold, airless interiors preserving these isotopes with near-perfect fidelity. Some grains even show spallation patterns, distinctive atomic rearrangements caused by exposure to galactic cosmic rays over eons. It's as if these asteroids were designed to hoard the universe's rarest chemistry. But here's the twist, some isotope ratios don't match any known stellar process. Take the excess chromium-50, found in certain meteorites. Its abundance is off the charts compared to predictions. One radical theory suggests it might be debris from a collision between neutron stars, an event so cataclysmic it briefly outshines entire galaxies, another possibility. These isotopes could be remnants of hypothetical strange stars, exotic stellar objects theorized to contain strange quark matter. If confirmed, asteroids wouldn't just be carrying stardust, they'd be holding evidence of physics beyond our current models. The implications stretch far beyond astronomy. These isotopes serve as tracers for mapping the solar system's raw materials. By comparing their ratios, we've learned that up to half of Earth's heavy elements, including gold and platinum, likely came from at least 2 different supernovae, plus a neutron star merger. It rewrites our origin story. We're not just children of the sun, but descendants of multiple stellar deaths. And the most tantalizing question remains, what other cosmic secrets are locked in these space rocks? Every sample return mission brings back isotopes we've never seen, each a clue to the universe's most violent and creative moments. Asteroids, it seems, aren't just rubble. They're the ultimate archivists of the cosmos, patiently waiting for us to decode their stellar whispers. Among the most perplexing sights on asteroids are the eerie, knife-edge ridges that stripe their surfaces, alien landscapes that look more like the work of an immense cosmic sculptor than random geology. The asteroid Eros, visited by NASA, a near-Shoemaker spacecraft in the late 1990s, revealed these formations in stunning detail. Near parallel crests stretching for kilometers, some standing taller than a 4-story building despite the asteroid's weak gravity. These aren't the chaotic fractures of impacts, but orderly structures that defy simple explanation. How could such precise features emerge on a world barely held together by its own gravity? One leading theory points to a slow-motion catastrophe, global cracking as Eros's interior cooled and shrank over billions of years. Picture a grape wrinkling into a raisin, but on a planetary scale. As the asteroid's core contracted, its brittle crust could have fractured in predictable patterns, creating the ridges we see today. Supporting this idea, many of Eros's ridges align with its major gravitational anomalies, hinting at deep structural connections. Yet there's a problem. Some ridges curve unnaturally, crossing each other in ways shrinkage alone can't explain. That's where impact stresses come in. When a massive collision shakes an asteroid, seismic waves ripple through its body. But in microgravity, the effects are bizarre. Instead of dissipating evenly, energy might concentrate along certain planes, forcing the surface to buckle in linear formations. The best earthly analogy, tossing a pebble into a dusty field and watching the powder arrange itself into radial patterns from the vibration. On Eros, these vibrational ridges could have formed during the same impact that created its giant 5-mile-wide Hymros crater, leaving behind ghostly imprints of the cataclysm. But the wildest hypothesis involves internal landslides. Unlike Earth, where gravity pulls debris straight down, Eros's weak tug about 1/1000th of ours allows material to slide for miles at shallow angles. Over eons, slow-motion avalanches might have piled debris into linear drifts, especially along the asteroid's equator, where centrifugal forces are strongest. Images even show some ridges adorned with boulders like pearls on a string, as if they'd rolled into place along invisible channels. The implications stretch beyond Eros. Similar ridges appear on asteroids like Bennu and Ryugu, suggesting this might be a universal process for small bodies. For future missions, these features could serve as roadmaps to an asteroid's seismic history, each crest a clue to past collisions or internal shifts. Some ridges even appear to funnel loose material into space, acting as natural launch pads for the dust streams we see around active asteroids. Yet the deepest mystery remains their resilience. In an environment where micrometeorite impacts should erode features within millions of years, how have these ridges persisted for billions? The answer might lie in their composition. Some could be cemented by hidden veins of stronger material, like the rebar in a concrete wall, quietly reinforcing them against the void's abrasion. Whatever their origins, these eerie formations remind us that even the smallest worlds harbor geology stranger than fiction, where the rules of earthly landscapes no longer apply, and every ridge tells a story written in the language of gravity's absence. Some asteroids refuse to play by the rules. Instead of sitting silently in the void, they crackle with unexpected activity, spewing clouds of gas and dust like miniature comets. Take 3,200 Phaethon, the bizarre blue asteroid responsible for the Geminid meteor shower. Unlike its rocky siblings, Phaethon belches out sodium vapor as it nears the Sun, creating a faint but measurable tail. This isn't supposed to happen. Asteroids are meant to be dry, inert relics, not dynamic worlds with atmospheres. So why is Phaethon and a growing list of others defying expectations? The mystery starts with temperature. When Phaethon swings closer to the Sun than Mercury, its surface heats up to over 700 degrees Celsius, hot enough to vaporize metals. Scientists suspect this extreme baking fractures its crust, releasing trapped sodium atoms in a process called thermal desorption. But here's the twist: sodium alone can't explain the sheer volume of debris in the Geminids. Something else must be loosening dust, and the leading culprit is rotational disintegration. As Phaethon spins, centrifugal force may fling surface material into space, creating the sparkling trails we see each December. Phaethon isn't alone in its theatrics. Asteroid 6478 Gault-stunned astronomers in 2019 when it sprouted not one but two tails, despite lacking ice comet's traditional fuel. The culprit, a delicate balance of sunlight and spin. Gault rotates so fast once every 2 hours that its surface barely holds together. solar radiation likely nudged loose boulders, triggering avalanches that launched dust into space. These active asteroids blur the line between comet and asteroid, proving that location alone doesn't dictate behavior. Even more puzzling are the rare main belt comets like 133P/Elst Pizarro. Nestled safely in the asteroid belt, far from the Sun's thawing reach, this object still manages to erupt occasionally with water vapor plumes. The leading theory suggests hidden pockets of ice lurk beneath its surface, shielded from sunlight for eons until impacts or landslides expose them to space. If confirmed, it means the asteroid belt could be dotted with secret reservoirs, rewriting our assumptions about where water survives in the solar system. The implications ripple across astronomy. Outgassing alters asteroids' orbits unpredictably, complicating impact risk calculations. For explorers, these gases could become resources. Imagine refueling missions by harvesting oxygen from asteroid plumes. But the biggest revelation, these aren't dead rocks. They're dynamic worlds where heat, spin, and hidden chemistry conspire to create phenomena we're only beginning to decode. Every hiss of gas, every ejected dust trail is a reminder. In space, even the quietest objects have voices, if we learn to listen. In the cosmic menagerie of asteroids, some defy the laws of celestial geometry, twisting into shapes so strange they look like children's clay sculptures tossed into space. Take Cleopatra, the notorious dog-bone asteroid cruising through the main belt. Radar images reveal a bizarre, elongated body with two bulbous lobes connected by a thin neck, stretching over 270 kilometers from end to end. This isn't just a quirk of perspective. Cleopatra's shape is so extreme, it challenges everything we know about how space rocks behave under gravity's gentle tug. How does an asteroid even form such a ridiculous silhouette? The leading theory involves a violent pass-adieu between two smaller asteroids. Imagine a slow-motion collision where two rocks graze each other, partially merging without fully combining, like cosmic Play-Doh pinched in the middle. Over time, their mutual rotation could have stretched the connecting region, sculpting that unmistakable dumbbell shape. Supporting this, Cleopatra spins rapidly, once every 5 hours, flinging loose material toward its equator, where two tiny moons now orbit like carousel riders. These moons, named Alex Helios and Cleoslene, might be debris ejected during the asteroid's formation, trapped in its gravitational ballet. But here's the twist: Cleopatra's density suggests it's not solid metal as once assumed. Despite its radar-bright surface indicating high metal content, the asteroid's overall mass is suspiciously low. Scientists now suspect it's a porous rubble pile, less a solid ingot and more a pile of rusty scrap metal loosely held together. This revelation upends traditional models of metallic asteroid formation, which assumed such bodies would compact under their own weight. Instead, Cleopatra implies even metal-rich asteroids can retain fragile, Swiss cheese interiors, defying expectations of how materials behave in microgravity. Cleopatra isn't alone in its oddity. The asteroid Itokawa resembles a half-melted snowman with two mismatched lobes clinging together. Then there's the spinning top-shaped Ryugu and its doppelganger Bennu, both looking like someone pressed their equators with a cosmic thumb. These forms hint at a hidden rulebook of asteroid evolution, one where rotation, collisions, and even sunlight conspire to sculpt bizarre profiles. The Yorp effect, for instance, can accelerate an asteroid's spin over millennia until centrifugal force reshapes it entirely, bulging the equator and pinching the poles like a cosmic potter's wheel. The implications ripple beyond curiosity. These shapes track an asteroid's history like tree rings. Cleopatra's twisted form suggests it survived a glancing blow that would have shattered a more rigid body. Ryugu's equatorial ridge points to a past spun so fast it nearly flew apart. For future missions navigating these irregular gravity fields where up might mean sideways will require entirely new approaches. Imagine landing on Cleopatra's neck, where the gravitational pull could vary wildly between lobes, turning a simple hop into a chaotic bounce. Yet the deepest mystery remains: how do these fragile oddities endure? In a belt where collisions are frequent, Cleopatra's delicate neck should have snapped billions of years ago. Its survival hints at unseen forces, perhaps van der Waals interactions between metal grains or electrostatic bonds, acting like cosmic glue. Every misshapen asteroid is a testament to the universe's whimsy, proving that even in the void, nature prefers the peculiar over the predictable. As we uncover more of these cosmic caricatures, one thing's clear: the asteroid belt isn't just a junkyard. It's an art gallery where gravity's brushstrokes have painted masterpieces of celestial absurdity. Glassy surfaces on asteroids aren't just cosmic curiosities, they're snapshots of moments when these quiet rocks briefly blazed with the heat of 1,000 suns. When Japan's Hayabusa 2 spacecraft touched down on Ryugu, it didn't just find rubble. It discovered patches of material so smooth and reflective, they shimmered like black ice under the probe's landing lights. These weren't natural erosion patterns. Spectral analysis revealed something extraordinary: tiny glass beads and melt splashes, the unmistakable fingerprints of sudden, violent heating. Someone, or rather, something, had flash-fried portions of Ryugu's surface in an instant, freezing them in time like cosmic fly trapped in amber, the culprit. Microscale meteorite impacts at speeds we can barely comprehend. Picture a grain of sand, no larger than a poppy seed, slamming into Ryugu at 50,000 kilometers per hour. At that velocity, kinetic energy converts to heat so intense it doesn't just melt rock. It vaporizes it on contact, sending shockwaves through nearby material. The surrounding regolith briefly liquefies, then cools almost instantly in the vacuum of space, leaving behind glassy veneers thinner than a human hair. Ryugu's glass isn't uniform. It forms intricate spiderweb patterns around microscopic craters, each one telling the story of a hypervelocity impact too small for telescopes to spot from Earth. But there's a twist. Some asteroids show glassy features on a far grander scale, defying the tiny impact explanation. Take Vesta, where NASA's Dawn mission found vast plains of volcanic glass near its south pole. These weren't formed by external bombardments, but by internal fury, lavas so rich in silica that they cooled into natural obsidian, mirroring Earth's volcanic glass deposits. The difference: Vesta's lower gravity allowed its lava fountains to spray droplets for kilometers, which hardened mid-flight into microscopic glass spheres. Centuries later, these same beads might have rained down on Earth as the mysterious tektites found in Australasian strewn fields, their chemical signatures eerily similar to Vesta's crust. The real stunner comes from Itokawa. Samples returned by Hayabusa 1 contained glass not from impacts or volcanism, but from solar baking. Over millennia, relentless sunlight appears to have partially melted minute flecks of metal in the asteroid's regolith, welding adjacent grains together into fragile glass-metal hybrids. It's a process so subtle, Earth's atmosphere would have prevented it entirely, proof that space weather can reshape asteroids in ways no terrestrial geology could predict. Why does this matter? Glass acts as a time capsule. Impact glasses trap bubbles of ancient solar wind, while volcanic varieties preserve traces of their parent magma's composition. For future explorers, these glossy patches could serve as natural mirrors for concentrating sunlight in power systems, or even raw materials for manufacturing in situ. But more profoundly, they reveal asteroids as worlds of hidden extremes where the gentlest touch of sunlight and the briefest kiss of interstellar dust can leave marks that last for eons. Every glassy surface is a paradox, a record of violence preserved in perfect stillness, waiting for us to decode its fiery origins. Some asteroids spin so fast they defy the very laws of physics holding them together, like cosmic figure skaters pulling off impossible pirouettes without flying apart. Take 2008 HJ, an asteroid barely wider than a football field that completes a full rotation every 42 seconds. That's a surface speed of nearly 200 kilometers per hour, fast enough to fling loose boulders into space if not for the asteroid's feeble gravity. And yet, somehow, it holds itself together. This isn't a fluke. Dozens of these fast rotators pepper the solar system, each challenging our understanding of how rubble piles behave under extreme stress. So how do they survive? The secret may lie in their peculiar internal structure. Unlike solid rocks, which would crack under such centrifugal forces, many fast rotators are loose collections of boulders bound by gravity and a surprising force called van der Waals attraction, the same microscopic stickiness that lets geckos walk up walls. Think of these asteroids as cosmic bags of gravel, where the spaces between rocks absorb the strain like shock absorbers. When 2008 HJ spins, its individual boulders shift slightly, redistributing energy rather than letting it build up to catastrophic levels. This flexibility turns what should be a fatal weakness into a bizarre strength, allowing these space rocks to rotate faster than should be physically possible. But there's a catch. Not all fast rotators fit this model. Some, like the 200-meter-wide asteroid 2015 TC25, spin even faster, once every 24 seconds despite appearing more solid. One radical theory suggests electrostatic forces could be at play here. As sunlight bombards these asteroids, it may charge their surfaces, creating attractive forces between particles that supplement gravity. Another possibility, they might be coated in ultra-fine dust that acts like cosmic Velcro, adding just enough cohesion to prevent disintegration. The implications are as profound as they are puzzling. Every time we discover another ultra-fast rotator, it forces us to reconsider where the limits of asteroid stability truly lie. Could there be asteroids spinning so fast they're nearly invisible, their surfaces blurred into a continuous haze by their own motion? And what happens when these cosmic speedsters collide? Models suggest a high-speed impact could spin up fragments to critical levels, creating new generations of fast rotators in a self-perpetuating cycle. Perhaps most remarkably, these asteroids serve as natural laboratories for studying the extremes of material science. Their survival hints at hidden properties of granular materials in microgravity, knowledge that could prove vital for future asteroid mining or even constructing rotating space habitats. As we uncover more of these celestial daredevils, one thing becomes clear. In the asteroid belt, the rules of physics aren't just bent, they're rewritten daily by rocks that spin on the edge of oblivion and laugh in the face of centrifugal doom. Hidden moons orbiting asteroids aren't rare anomalies, they're shockingly common, rewriting what we thought we knew about these small celestial bodies. When NASA Galileo spacecraft flew past the asteroid Ida in 1993, it spotted a tiny companion, Dactyl, marking the first confirmed asteroid moon. What seemed like an astronomical oddity turned out to be just the beginning. Fast forward to today, and we've discovered over 400 asteroids with moons, including some with entire binary or even triple systems dancing around each other in the void. The asteroid Electra, for example, boasts not one but 3 moons, a record that makes this space rock more akin to a miniature planetary system than a lonely boulder. How do these tiny worlds capture or retain moons despite their weak gravity? The answer lies in their chaotic past. Many asteroid moons likely formed from debris ejected during colossal collisions. When 2 asteroids collide at cosmic speeds, the impact can send fragments spiraling outward. Some escape entirely, while others remain trapped in orbit, settling into stable paths over millennia. Others might be captured during close encounters, where a passing rock slows just enough to be snared by an asteroid's gravitational pull. The asteroid Didymos and its moon Dimorphos, famously targeted by NASA's DART mission, probably formed this way, with Dimorphos likely being a chunk of Didymos itself, dislodged long ago. But here's where it gets even more intriguing. The presence of moons doesn't just hint at past violence, it actively shapes the asteroids themselves. Tidal forces from these orbital partners can induce seismic tremors, triggering surface landslides or even altering the primary asteroid's spin rate over time. Some moons, like the one orbiting the asteroid Eugenia, are so massive relative to their parent that the pair actually orbit a shared point outside the main body's surface, a configuration that challenges traditional definitions of what constitutes a moon versus a binary partner. The discoveries keep piling up. The Lucy mission's flyby of the asteroid Polymel revealed an unexpected satellite, forcing scientists to rethink how small and faint these moons can be. Some are mere city blocks in size, barely detectable from Earth except during rare occultation events when they briefly block distant stars. Others, like the moon of asteroid Florence, orbit so closely that their mutual gravitational dance distorts both bodies into stretched egg-like shapes. Beyond their scientific allure, these moons have practical implications. Their orbits allow us to calculate asteroid masses with precision, revealing whether these objects are solid rock or porous rubble piles. For planetary defense, understanding moon dynamics is critical. A rogue asteroid with a moon might require different deflection strategies than a solitary one. The real revelation: these unassuming moons are clues to the solar system's violent adolescence. Each one is a fossil of ancient collisions that shaped the asteroid belt. As we uncover more, they remind us that even the smallest worlds can hold hidden complexities, gravity's miniature masterpieces, silently orbiting in the dark. Deep within certain asteroids, scientists have found tiny time capsules older than our sun, grains of stardust forged in the violent deaths of ancient stars. These microscopic specks, some no larger than a red blood cell, date back over 7 billion years, making them the oldest solid materials ever discovered. When NASA's Stardust mission analyzed particles from comet Wild 2, and later when Japan's Hayabusa 2 brought back samples from Ryugu, they uncovered silicate and carbon grains with isotope ratios so alien they couldn't have formed in our solar system. These are literal pieces of other stars preserved with near-perfect fidelity in the frozen vaults of space rocks. What makes these grains so extraordinary is their origin story. Most formed in the fiery winds of red giant stars or the cataclysmic explosions of supernova, events that occurred long before our solar system's birth. As those dying stars ejected their material into the cosmos, some of it drifted into the molecular cloud that eventually collapsed to form our sun and planets. But instead of being vaporized and recycled, these stubborn grains survived embedded in asteroids like cosmic fossils, shielded from heat and radiation for billions of years. Their chemistry is a direct window into the nucleosynthesis processes of stars that died before Earth even existed. The real shock came when researchers analyzed their crystalline structures. Some presolar grains contain microscopic diamonds formed in the shockwaves of supernova. Others, like silicon carbide, display unusual isotopic signatures of heavy elements like xenon and barium, proof they condensed in the outer atmospheres of carbon-rich stars. A rare few even carry traces of neon E, a neon isotope that only forms in the heart of supernova under conditions so extreme they defy laboratory replication. These aren't just old rocks, they're pieces of stellar alchemy, physical evidence of how stars forge the elements that make up everything from planets to people. But here's where the mystery deepens. Some of these grains shouldn't exist at all. Take the so-called gems, grains, glass with embedded metal and sulfides found in interplanetary dust. Their nanostructures suggest they formed in the cold, diffuse interstellar medium far from any star. Yet they're riddled with isotopic anomalies indicating exposure to multiple stellar environments. The leading theory: these grains might be cosmic patchworks assembled from the debris of several different stars over eons before being incorporated into asteroids. It's as if the universe wove together fragments of its own history into these minuscule mosaics. The implications stretch beyond astronomy. By studying these grains, we've learned that our solar system likely formed from a peculiarly enriched patch of the galaxy, one seeded by the explosions of multiple generations of stars. Some models now suggest a nearby supernova may have even triggered the collapse of our natal molecular cloud. Each speck of ancient stardust is a clue to the cosmic neighborhood we were born in and the violent stellar drama that made our existence possible. Perhaps most poetically, these grains remind us that we're literally made of the same star stuff. The carbon in your cells, the iron in your blood, and the calcium in your bones were all forged in distant stellar furnaces, then delivered to Earth by the same asteroids that preserved these primordial time capsules. Every time we hold a meteorite fragment, we're touching relics that witnessed the galaxy's golden age, silent messengers from an era before light, before planets, before time as we know it began. And the astonishing truth, there are still older grains out there waiting in the asteroid belt's dark vaults, carrying stories we've only begun to decipher. Certain asteroids carry invisible fingerprints, magnetic signatures so peculiar they defy straightforward explanation. Take 21 Lutetia, a hefty asteroid visited by ESA's Rosetta spacecraft in 2010. As the probe zipped past, its instruments detected patches of remnant magnetism, ghostly echoes of a magnetic field that shouldn't exist in a body of its size. Unlike Earth, where our magnetic dynamo is powered by a churning molten core, Lutetia lacks the mass and internal heat to sustain such processes. Yet there it was, whispering magnetic secrets that sent scientists scrambling for answers. One compelling theory traces these anomalies back to the asteroid's violent infancy. Imagine Lutetia as a fragment of a far larger protoplanet, one with a molten metal core capable of generating a planet-scale magnetic field. If this parent body shattered during the solar system's chaotic early days, Lutetia could have inherited pockets of magnetized material frozen in time as its molten interior suddenly cooled. It's like finding a single glowing ember from an ancient forest fire, still clinging to heat after millennia. Supporting this, Lutetia's density and composition suggest it was once part of something bigger, with a differentiated interior that might have briefly harbored the conditions for magnetism. But here's where the plot thickens. Some of Lutetia's magnetic patches don't align with this simple narrative. Instead of being uniformly distributed, they cluster in strange, asymmetric patterns, almost as if the asteroid had been magnetized from the outside rather than within. This raises a radical possibility. Lutetia might have been temporarily magnetized by an external field, perhaps from the young sun's own powerful magnetic influence during the solar system's formation. Picture the asteroid passing through a cosmic forge, its minerals realigning like iron filings near a magnet, then locking those properties in place as it cooled. The implications ripple beyond Lutetia. Similar anomalies have cropped up on other asteroids like Eros and even the tiny Itokawa. Each case offers clues about the environments these objects endured billions of years ago. Some researchers now suspect the early asteroid belt was a magnetic playground, crisscrossed by fields generated by the sun's turbulent youth or even near by plasma shocks from stellar explosions. Asteroids, it seems, could be recording devices for these vanished forces, their minerals preserving data about conditions we can't replicate or observe directly. What's more, these magnetic quirks might solve a long-standing meteorite mystery. On Earth, certain chondrite meteorites show remnant magnetism that doesn't match our planet's field. If they originated from asteroids like Lutetia, their magnetism could be a relic of their parent body's histories, not Earth's. It's a paradigm shift. Instead of being passive rocks, asteroids actively encode the solar system's magnetic past in their atomic structures. The next time you look up at the night sky, consider this. Some of those drifting asteroids are more than inert rubble. They're cosmic archivists, their silent surfaces hiding invisible tales of primordial forces that shape not just their own stories, but potentially the very foundations of our planetary neighborhood. Some asteroids might not be the dry, barren rocks we imagine hidden inside their dark, carbon-rich exteriors could be remnants of a primordial slush, a sticky mixture of water, organics, and minerals that once oozed through their veins. This mudball theory is turning heads in planetary science, suggesting that certain asteroids, particularly those in the C-type family like Ryugu and Bennu, began their lives as soggy, clay-heavy masses rather than solid stone. Picture a cosmic snow cone, but instead of ice, it's a messy amalgamation of water, ammonia, and carbon compounds, slowly freezing over billions of years into the fractured rubble we see today. How did these mudballs form? The clues lie in their chemistry. When scientists analyzed samples from Ryugu, they found minerals like serpentine and saponite clays that only form in the presence of liquid water. But here's the twist. These asteroids are too small to have generated the heat needed to melt ice internally. Instead, the water likely came ready-made, trapped in the dusty debris of the solar nebula. As these asteroids coalesced, radioactive decay or residual heat from formation could have briefly thawed their icy interiors, creating a slurry of mud that percolated through the rock, reshaping its structure. Over time, as the heat faded, the slush refroze, leaving behind telltale mineral veins and pore spaces that missions like Hayabusa 2 and OSIRIS-REx are now uncovering. The implications rewrite early solar system history. If mudballs were common, they could have been delivery vehicles for water and organic molecules to young planets like Earth. Unlike comets, which often vaporize their ices in dramatic tales, these asteroids might have gently sweated their water into space through cracks and vents, seeding planets with life's ingredients in a slow, steady drip. Some models even suggest that the water in your glass right now might have originated in one of these soggy space rocks, transported during the chaotic era of planetary bombardment over 4 billion years ago. Yet the mudball theory isn't without controversy. Critics point out that some carbon-rich asteroids show no evidence of past water alteration, hinting that conditions in the early solar system were far patchier than we assumed. Others propose that the water wasn't indigenous at all. It might have been injected by later impacts from icy bodies, turning dry asteroids into temporary mudballs long after their formation. The debate hinges on upcoming missions like NASA's planned visit to the asteroid Psyche, which could reveal whether water-bearing minerals are the rule or the exception among dark, carbon-rich asteroids. What's undeniable is the sheer weirdness of these objects. Imagine drilling into one and finding not rock, but a spongy matrix of ancient clays, still smelling faintly of ammonia after eons in the deep freeze. Or stumbling upon a pocket of preserved organic goo, untouched since the dawn of the solar system. These aren't just scientific curiosities, they're time capsules from an era when the building blocks of planets were still figuring out how to assemble. Every muddy asteroid we study peels back another layer of the solar system's recipe book, revealing a story where water, rock, and carbon danced together long before Earth even existed. And the most tantalizing question remains: if these cosmic mudballs were so good at preserving life's ingredients, could they have secretly incubated life's earliest steps in their dark, soggy interiors? The answer, much like the asteroids themselves, might be messier and far more fascinating than we ever dreamed. Imagine an asteroid so dramatically reshaped by ancient violence that its entire surface now wears its scars upside down, like a cosmic jigsaw puzzle reassembled wrong. This is the bizarre reality of asteroids like Bennu, where vast regions appear geologically flipped, with material that should be buried deep now lying exposed while older surfaces hide underneath. When NASA OSIRIS-REx mission mapped Bennu in detail, scientists expected to find a predictable layer cake of geology, older bedrock covered by newer impact debris. Instead, they confronted chaotic jumbles where boulders from the asteroid's interior sat atop younger terrain, as if some cosmic hand had peeled the asteroid open and stitched it back together haphazardly. The culprit, catastrophic impacts powerful enough to send seismic waves rippling through Bennu's fragile rubble pile structure. Picture a pebble dropped into loose sand, except in this case the pebble is a kilometer-wide impactor and the sand is an entire asteroid. Such collisions wouldn't just carve craters, they'd trigger global earthquakes, churning the surface like a snow globe. On a low-gravity world like Bennu, where boulders barely cling together, these tremors could flip entire sections of terrain, burying once exposed surfaces while exhuming material from hundreds of meters below. Some flipped fragments might even carry pristine organic compounds untouched by space weathering, suddenly thrust into sunlight after billions of years in darkness. But here's the twist: Bennu's flipped terrain isn't uniformly jumbled. Certain regions, like the oddly smooth Nightingale crater, show precise inversions where distinct layers appear reversed, older deposits overlapping newer ones in knife-sharp boundaries. This suggests the flipping wasn't random chaos, but an eerily organized process where seismic energy focused along hidden fault lines, like a tablecloth yanked from beneath a dinner setting. Scientists liken it to a planetary scale magic trick. The asteroid didn't just get stirred, it performed a calculated sleight of hand, preserving delicate structures even as it turned itself inside out. The implications stretch far beyond Bennu. Similar flipped surfaces appear on Ryugu and even small moons like Phobos, hinting that this phenomenon might be a universal feature of rubble pile bodies. For geologists, these asteroids are like shuffled decks of cards, each flipped boulder a clue to reconstructing the original sequence of events. Some inverted layers might preserve snapshots of the solar system's chemical composition at specific epochs, while others could reveal how asteroids transport and protect water-bearing minerals during collisions. Yet the deepest mystery isn't how these surfaces flipped, it's why they stayed that way. In Earth's gravity, flipped terrain would quickly erode, but asteroids' feeble pull lets these upside-down landscapes persist for eons. Walking across Bennu would be like traversing a frozen earthquake. One misstep, and you might stumble from a billion-year-old exposed core sample onto a freshly deposited landslide. These cosmic upheavals remind us that even the smallest worlds harbor geology as dynamic as any planets, where the violence of the past isn't buried, but written in plain sight, waiting for us to decipher its topsy-turvy language. The surfaces of some asteroids look like they've been sandblasted by an invisible cosmic hand, etched with strange, swirling patterns that tell tales of relentless solar bombardment over billions of years. These aren't ordinary impact scars or random cracks. They're the result of the solar wind, that relentless stream of charged particles hurled outward by the sun at speeds topping 800 kilometers per second. Over eons, this invisible force has sculpted asteroid surfaces into alien landscapes, leaving behind textures so distinct they're like fingerprints of deep space exposure. Take the asteroid Eros, for example. Close-up images from NASA's near-Shoemaker mission revealed vast plains dotted with peculiar streamers, thin, wispy streaks of brighter materials stretching across its surface like cosmic brushstrokes. These aren't geological features in the traditional sense. They're the aftermath of solar wind particles slamming into Eros's surface, knocking atoms loose and redistributing minerals in a process called space weathering. The solar wind's charged particles, mostly protons and electrons, act like microscopic sandpaper, preferentially eroding darker, carbon-rich materials while leaving behind reflective metallic grains. The result, a patchwork of bright and dark zones that shift over millennia, creating those ghostly patterns. But here's where it gets even more fascinating. The solar wind doesn't just weather asteroids uniformly. Magnetic anomalies like those found on the asteroid Braille can deflect charged particles, creating shielded zones where the surface remains pristine. It's as if these space rocks have natural sunblock patches areas protected from the solar wind's erosive effects, preserving ancient material untouched by space weathering. Meanwhile, on airless bodies like the Moon, solar wind implantation actually creates water molecules by bonding hydrogen ions to oxygen in surface minerals. Could the same process be hydrating asteroids, leaving behind trace water in the most unexpected places? The most dramatic evidence of solar wind sculpting comes from rinded asteroids, those with surfaces that appear strangely glassy or melted. High-energy particles, especially during solar flares, can fuse the uppermost dust layers into a thin, brittle crust, almost like the caramelized top of crème brûlée. Japan's Hayabusa 2 mission spotted this phenomenon on Ryugu, where some boulders sported bizarre, shiny veneers. These glassy rinds aren't just cosmetic, they're time capsules recording the intensity of solar activity across epochs. Cracks in the crust caused by thermal stresses even allow scientists to estimate how long the surface has been exposed, like counting tree rings, but for space weathering. What's truly mind-bending is how these scars influence asteroid colors over time. Freshly exposed surfaces, like those in recent impact craters, often appear bluish or neutral gray. But as solar wind bombardment continues, they gradually redden as tiny iron nanoparticles form in the damaged mineral lattice. This explains why older asteroids like Itokawa have a distinctly reddish hue compared to younger fracture zones. It's a slow mutation process, one that turns these wandering rocks into cosmic chameleons, their colors shifting with every eon spent bathing in the solar wind. Yet the solar wind's artistry isn't just destructive. It might also be the reason certain asteroids have such unusual shapes. Over millions of years, uneven erosion from angled particle flow could sand down one side of a spinning asteroid more than the other, sculpting it into a flattened or elongated form. The Yorp effect, where sunlight nudges an asteroid's rotation, could team up with solar wind weathering to create bizarre geometries. Imagine a space rock slowly carved into a jagged wedge or a smooth, wind-worn pebble, its contours shaped by the invisible rivers of the solar wind. As missions return more samples from asteroids like Bennu and Ryugu, we're learning just how deeply the solar wind's fingerprints penetrate. Some grains show evidence of radiation damage stretching micrometers below the surface, proof that these particles don't just skim the exterior, they can alter chemistry at the atomic level. For future explorers, this means asteroid resources might need to be mined from beneath heavily weathered layers to access pristine material. But perhaps the most poetic realization is this: every strange swirl, every glassy patch, every reddish slope is a testament to endurance. These asteroids have weathered not just the physical storms of space, but the silent, ceaseless gale of the solar wind, a wind that's been blowing since the sun's first flickers of life. Their scars aren't just damage, they're the hieroglyphs of deep time, written in a language of charged particles and atomic shifts, waiting for us to translate their stories. Beneath the seemingly lifeless surfaces of some asteroids lies a hidden engine of radioactive decay, a slow-burning power source that once turned these cold rocks into dynamic, geologically active worlds. Take Vesta, the second largest asteroid in the belt, whose surface is littered with volcanic basalt plains. These lava flows shouldn't exist on such a small body unless something generated intense internal heat. The culprit, isotopes like aluminum-26 and iron-60, radioactive elements that were abundant in the early solar system. When these isotopes decay, they release energy, enough to melt ice, liquefy rock, and possibly even fuel subsurface hydrothermal systems for millions of years. The process works like a cosmic battery. As aluminum-26 decays into magnesium-26, it emits gamma rays and heat, raising temperatures by hundreds of degrees. In larger asteroids like Vesta or Ceres, this heat could have persisted long enough to differentiate their interiors, separating metals from silicates and allowing lava to erupt onto their surfaces. But even smaller asteroids might have experienced brief flashes of geologic vitality. Imagine a space rock just 50 kilometers wide, its core simmering at 800 degrees Celsius, with radioactive decay cooking its interior like a slow oven. Over time, that heat would dissipate, leaving behind telltale mineral signatures, chlorine-rich veins, metamorphosed clays, and oddly layered interiors that missions like Dawn and Hayabusa 2 are now uncovering. Here's the twist: this heat didn't just shape asteroids, it might have primed them for chemistry. On Earth, hydrothermal vents are crucibles for life, where heat, water, and minerals interact to form complex organics. Some radioactive asteroids, especially those with ice, could have hosted similar environments. Picture a carbon-rich asteroid with pockets of melted ice, its warm, briny fluids percolating through fractures, rearranging molecules into amino acids or other prebiotic compounds. Japan's Hayabusa 2 team found hints of this on Ryugu, where certain carbonate minerals only form in the presence of liquid water and heat. It's a tantalizing possibility that the same radioactive decay which melted these asteroids might have also stirred the pot for life's ingredients. Yet the real shocker is how recently some of this activity might have occurred. While most assume asteroid heating was an ancient phenomenon, modeling suggests smaller bodies could have stayed warm far longer than expected, perhaps even into the era when life was first emerging on Earth. The asteroid Bennu, for instance, shows mineral evidence of past water alteration that might date to less than 1 billion years ago. If confirmed, it means the solar system's smallest worlds were still geologically alive long after the planets had settled into their current forms. What's left today are the ghosts of this radioactive past. Asteroids like Psyche bear the scars of their heated youth in their metallic cores, while others, like Mathilda, are frozen time capsules with uranium and thorium still decaying in their interiors at a glacial pace. Future missions could map these residual heat signatures, pinpointing which asteroids were once miniature furnaces and which might still harbor whispers of warmth beneath their surfaces. The lesson here is profound. Size doesn't always dictate destiny. Even the humblest asteroid, given the right nuclear spark, could briefly rival the geologic drama of planets. And as we dig deeper into their radioactive histories, we're reminded that the solar system's most unexpected transformations often happen in the quietest corners, where atomic decay writes stories of fire and rebirth in the dark. Among the most explosive debates in planetary science is the claim that certain asteroids might carry traces of extraterrestrial life, not in the form of organic precursors, but as actual fossilized microbes. The controversy centers on a handful of meteorites, like the infamous LH-84001 from Mars and the lesser-known Augale meteorite from an unknown asteroid. When examined under high-powered microscopes, some researchers have identified minuscule structures resembling fossilized bacteria, complete with segmented cells and chain-like formations eerily similar to terrestrial microbial colonies. If proven authentic, these could be the first physical evidence of life beyond Earth, but the scientific community remains fiercely divided. The case for ancient asteroid microbes hinges on several lines of evidence. In the Augale meteorite, a carbon-rich relic from the early solar system, scientists found tubular and filamentous structures embedded in clay minerals. These resemble Earth's iron-oxidizing bacteria, suggesting similar life might have thrived in water-rich asteroids. Even more compelling are the isotopic ratios in these features, unusual concentrations of carbon-13 and nitrogen-15 that typically signal biological processing. Proponents argue that non-biological processes couldn't produce such intricate structures with such distinctive chemistry. Some even point to amino acids in these meteorites that exhibit homochirality, a preference for left-handed molecules, a trait considered a hallmark of life. Skeptics, however, fire back with equal intensity. They note that many microfossils are orders of magnitude smaller than any known Earth bacteria, raising doubts about how such organisms could function. Others demonstrate how abiotic processes like the self-assembly of minerals under hydrothermal conditions can create lifelike shapes. The famous nanobacteria debate of the 1990s looms large here, when similar microscopic structures in Martian meteorites were later shown to form without biology. Even the isotopic anomalies have alternative explanations. Cosmic ray bombardment or exotic chemistry in the protoplanetary disk could mimic life's fingerprints. The debate takes a wilder turn with claims of living microbes in asteroid material. In 2020, Japanese researchers reported detecting dormant, ultra-tiny organisms in Ryugu samples that revived when exposed to water, though most scientists attribute this to earthly contamination. Meanwhile, experiments show certain extremophiles can survive embedded in artificial meteorites during atmospheric entry, muddying the waters further. Underlying this clash is a fundamental question. If life did arise independently in asteroids, how? Some theories propose radioactive gardens, where decay heat melted ice into transient pockets of water, while others suggest panspermia, that life's building blocks hitched rides between worlds. Either way, the implications are staggering. Asteroids wouldn't just be life's delivery trucks, they'd be incubators, proving the universe is far more inventive than we dreamed. For now, the verdict remains suspended. New missions like ESA's Hera and NASA Mars sample return may provide clearer answers, but one thing's certain: these tiny structures, real or imagined, have already transformed how we see asteroids, not as dead rocks, but as potential graveyards or even cradles of life's first whispers. From metallic cores exposed like cosmic wounds to asteroids spinning so fast they should tear themselves apart, these 25 discoveries have shattered our simplest assumptions about the solar system's rubble. We've stumbled upon water ice clinging to sun-scorched rocks, organic molecules defying the harshness of space, and magnetic ghosts whispering of ancient planetary chaos. We've seen asteroids shaped like dog bones, streaked with glass forged in interstellar collisions, and even suspected of hiding the fossilized echoes of extraterrestrial life. Each revelation peels back another layer, proving these aren't just dead rocks, they're time capsules, laboratories, and perhaps even cradles, rewriting the story of how our cosmic neighborhood came to be. These findings force us to rethink the asteroid belt's role in the solar system's grand narrative. No longer mere debris, these bodies are active participants delivering water to planets, mixing organic chemistry in their muddy interiors, and preserving stardust older than the sun itself. They've shown us that planetary formation wasn't a tidy process, but a messy ballet of violence and chance, where worlds collided, melted, and reassembled into the oddities we see today. Even their fragility holds lessons. Rubble piles and hollow caverns reveal how gravity's faintest whisper can sculpt landscapes stranger than any sci-fi vision. But the most thrilling thought: we've barely scratched the surface. Imagine what else lurks in the dark: subsurface oceans, exotic matter we've yet to name, or even evidence of life's cosmic ubiquity. With missions like Psyche and Hera launching soon, the next decade promises discoveries that'll make today's revelations seem quaint. So tell us, what do you think is still out there waiting to be found? A fragment of an alien civilization, a mineral that defies physics? Drop your wildest theories below, and don't forget to subscribe. The universe's weirdest secrets are still hiding in plain sight, and together we'll uncover